Welcome everyone to today's webinar. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. And today our topic is on exploring thermal properties with frequency and time-domain thermoreflectance. This is a guest webinar here. I'm fortunate to be joined by James Pomeroy, co-founder of Thermap Solutions. He's really going to be taking us through the bulk of today's content here after I wrap up with a quick introduction. So with that being said, we'll get going with that, and then I'll be handing it over to James here shortly. Just for the folks that may be new to these types of webinars, C-Therm in general, just want to give a quick introduction about who we are and what we do. So C-Therm Technologies, we focus on the transient class of thermal conductivity measurement technique. Really our purpose and what our goal in developing and offering these methods is to simplify thermal conductivity testing for the materials of tomorrow. Now, our core instrument platform is called Trident. You can see this here. Trident was developed as a modular solution, bringing together 4 different methods for thermal conductivity testing. These different methods, these different sensor types really allow for a broad range of material characterization, whether that's solids, non-solids, low, high conductivity. The ability to pick and choose the best method based on the specific application or the task at hand is really the idea behind the development of this instrument. Now, of course, it's not going to be the focus of today's talk, but just for those that may be interested in wanting to learn more, I'm certainly happy to provide additional information if needed. This quote here, we always like to share it. This really does embody the idea behind Trident. The quote from Abraham Maslow, when all you have is a hammer, everything looks like a nail. The idea that time and time again, we see groups that may be dealing with, again, a very diverse sample sets, different, again, liquids, powders, pastes, whatever that may be. And when you're trying to basically fit everything in towards one method, this is where issues come up in data quality, repeatability, etc. So again, this quote really embodies the idea behind Trident, giving you that flexibility to do more of a toolbox approach in addressing your testing needs. Now, all that being said, for folks that whether you're new to thermal conductivity or maybe you've been in the space for a while but just kind of looking for a refresher on what's out there, we do have this method selection guide available as a free resource download. It's a great document. It was recently updated at the end of last year. Really goes over all of the methods that we offer on Trident, but of course other methods that exist in industry, steady state, actually some of the time domain and frequency domain reflectance measurements that we'll be talking about today as well. So it's a nice little resource to take a look at. Definitely worth checking out if you haven't already done so. But that being said, that kind of wraps it up for my quick little introduction here. At this point, like I said, really, I'm going to pass the floor over to our guest speaker here today, James Pomeroy, to take us through the bulk of today's session. So over to you, James. Thank you.
Thank you very much for the introduction, and also thank you to C-Therm for organizing this webinar. Just give me a moment, I will share my screen. Okay, good. Do you see my screen? Just check before I start.
All good, looks great.
Okay, excellent. Yep, so yeah, it's my pleasure to be here today to represent Thermap Solutions. And over the next 30 minutes or so, this webinar is going to be exploring how to measure thermal properties with frequency and time-domain thermoreflectance. Okay, so yeah, just before we get started, an outline so you know what to expect. So we'll start with a more sort of top level view, so an introduction to Thermap, what we do, which is frequency and time-domain thermoreflectance. And I explained a little bit about the platform that we have, the instrument platform and the software I use for analysis. And yeah, a very top level view of a comparison between the capabilities of our nanosecond time-domain thermoreflectance and frequency-domain thermoreflectance. And then after that, we'll get into more technical detail about what thermoreflectance is, how nanosecond and TDTR and FDTR work, covering the basic principles. Then the concept of thermal diffusivity and how that relates to the depth probe versus time or frequency. How thermal properties are determined by fitting the data. And then the second half is really looking at application examples where we found nanosecond TDTR and FDTR to be useful. So Thermap is a spin-out from the CDTR at the University of Bristol in the UK. And we focus on manufacturing laser-based thermal property metrology tools. And we also provide materials analysis service. So the research group itself has about 2 decades heritage in thermal characterization of semiconductor devices, TIMs, semiconductor packaging materials, also composites. But we had more and more inquiries from industry to do measurements and a lot of interest in the techniques that we're developing in the lab. So at that point, we were very motivated to take these techniques, these tools which are developed in a research context, and then put them into an easy-to-use turnkey solution that could be used in industry. And the output of that is the instrument shown on the right-hand side. Over the years, we've collaborated with numerous research institutes, companies, customers, other ones that we can mention. Okay, so why do we need to develop new techniques at all? So in a lot of emerging applications, like semiconductors, composites, coatings for aerospace, nuclear, energy storage, which was mentioned previously, there are multiple layers, complicated structures, and layer thicknesses can be ranging from hundreds of nanometers to millimeters. So on the right-hand side is an example of a packaged semiconductor device. That's just one example, but you can see that it's a layered, complex structure. And our priority really is to measure the thermal properties of the individual layers, but also the interfaces between them in situ, without having to disassemble a part. And the key point really is that if you take bulk properties and you apply them to these assemblies, they won't always be reliable because of the way the processing is done. Things like die attach or bonding between materials, it's very process dependent. So yeah, our priority is really to measure the assembly in situ, thermal properties in situ. So our tools are really aimed at this, to measure with depth resolution and lateral space resolution, which is compatible with these length scales. So there's obviously existing approaches like laser flash, but it's difficult or impossible to separate multiple layers in a measurement. And also, you need to prepare the sample into a set size, which is destructive. So another thing that we always try to do is to keep sample preparation to the minimum and have a lot of flexibility in terms of the size of the sample. Okay, so that's kind of the motivation for what we do. Now, before getting into more detail about how these things work, I just want to show a table which summarizes the capability, what's offered by the nanosecond time-domain thermoreflectance and the frequency-domain thermoreflectance. So the nanosecond TDTR is really tailored to high lateral spatial resolution and thinner layers. So we have a smaller laser spot and we're measuring faster transients. Whereas the low frequency FDTR, we use larger laser spots and measure at lower frequencies, so we can probe thicker layers. And there's obviously some overlap between them. So depending on the application, it can be TDTR and or FDTR is applicable. We can handle large samples. We can make temperature-dependent measurements, bulk samples or multi-layered samples. We can fit multiple unknowns, including density, specific heat, thermal conductivity. Typically, we can measure up to 3 parameters simultaneously. We'll come back to that a little bit later, what the restrictions are there. Anisotropic materials can be measured. And then another important distinction between these two is that the TDTR technique requires a reflective sample, so that sometimes requires polishing if you have a rough sample, whereas the FDTR, we can measure rough and even non-flat surfaces. So here's just an example of 2 measurements underway on the left-hand side with the TDTR. So this is semiconductor wafer. You can see that it's reflective. Whereas for the FDTR, yeah, we can accommodate things, very unusual samples. So this is a 1 millimeter spherical particle measuring thermal conductivity without any special sample preparation. So curved surfaces and rough surfaces possible. Okay, so it's very important to ensure accuracy. We do that by comparing to standard reference materials where we know the thermal properties well. So this plot showing that. Just to point out here that we can also measure thin, very high thermal conductivity materials. So the TM100 is a CVD diamond product, which is 300 microns thick. That can be challenging using other techniques. So this is what the instrument looks like. So this is our modular platform. So this can be configured for the TDTR, FDTR, and depending on the customer's requirements or the application requirements, we can select different wavelengths, different optics, different laser spot sizes, depending on the spatial resolution required. And all the lasers, the detectors, electronics are contained within the same enclosure, so it's compact. And at the front, you see the mapping stage, objective lens on a turret, which can be changed, and a camera above. Yeah, and it's basically a simple push button operation from a PC. So it's designed to be very easy to use. So historically, these techniques have had a reputation for being quite complex and requiring a lot of expertise. So yeah, we've from the start of the design, we've prioritized ease of use and stability. Okay, so the user interface, so the application itself looks like this. So this tab shown is for the FDTR measurement. So there's some details here which become a little bit clearer later when we get into the sort of the technical aspects. But essentially, the user will set up the sample in the top left, so entering the layer structure. So each layer, the thermal properties can be inputted from a database or entered manually. And then the user will indicate which properties are unknown and to be fitted in the analysis. Bottom left is a navigation window, so we have a camera. We can move the stage in X, Y, and Z. The central window is the sort of just the data plot. So as the data is acquired, it's plotted on the screen, and then automatically a model is fitted to the data to extract the required unknown thermal properties, which are reported in the bottom table. So this is FDTR, so it's frequency versus phase. We'll come on to what that means a bit later. But essentially, it's some data which is acquired and fitted with a model, a heat diffusion model, to extract the thermal parameters. And then there's a corresponding window for the TDTR measurement mode, which looks exactly the same apart from the data, which is plotted is on a time scale. But essentially, the operation is the same. Okay, so yeah, so if there's anyone on the call who's not familiar with thermoreflectance, the basic principle is that the reflectivity of materials changes as a function of temperature, and for small temperature changes, we say it's proportional to temperature change, and that proportionality is described by this thermoreflectance coefficient, CTR, and that's material dependent and it's wavelength dependent. So for a particular material, you can select a wavelength which will give you a good response. So that means that if you change temperature, there's a measurable change in reflectivity. So yeah, it's a fairly small coefficient. So sensitive low noise detection is required. So that's something we've worked on a lot to really reduce the noise in the measurement data. Yep, so we can select a wavelength which is suitable to the material to give a high enough response, or we can coat the sample with a standard material. So we often use 100 nanometer thick gold coating, and you can see from the plot on the right-hand side that this gives us a high coefficient for blue or green wavelengths. Okay, so by probing the change in temperature when we heat it with another laser, from that we can determine unknown thermal properties. Again, we'll come on to that later, exactly how that's done. But an important thing to note here is that we're not measuring absolute temperature. We're measuring a relative change in temperature, which in the end is a relative change in reflectivity. So we don't need to do calibration per sample, which you do have to do if you want to measure absolute temperature change. So it's relatively much simpler just to measure the relative change, which is what we do. So no calibration per sample. We just have to ensure that there's a measurable change in reflectivity. Okay, so transient thermoreflectance measurement basics. So it's a family of pump probe laser-based techniques, and we have one laser which is a heating laser, which is pulsed or modulated, so that heats the surface. And we have another laser, CW laser, which is reflected from the surface, and the reflectivity change is proportional to the surface temperature change. And within that surface temperature change versus time is encoded the thermal properties, information about the thermal properties of each layer in the sample. Okay, so we can use thermoreflectance to measure thermal conductivity in plane and cross plane, thermal boundary resistances between the layers, but also layer thicknesses and heat capacities can be obtained. Yeah, and the unique thing here is that we can measure multiple layers simultaneously. So starting with the nanosecond time-domain thermoreflectance. So in our implementation, we use 3 nanosecond heating pulses. This is the pump pulse shown here in the diagram. So that heats the surface for a short duration. And then with the probe laser reflected from the surface into a photodetector, we monitor the change in reflectivity. So a key thing here is that we need to think of time as depth. So at 0 time, we're just heating the surface. And as we go to longer time, the heat is diffusing through the sample. We're sensitive to deeper layers further from the surface. So we get information about multiple layers and multiple interfaces. So taking that transient, we fit an analytical heat diffusion model, and then we can obtain the unknown parameters. And this technique is really tailored to thinner films with higher spatial resolution. So we're talking up to 10 microns depth and spatial resolutions down to 1 or 2 microns. And then frequency-domain thermoreflectance. So the principle is very similar, but now we're modulating the laser heating at a set frequency, and then the probe laser is reflected, and we're measuring the phase of the reflected signal. So the phase shift of the surface temperature change. And again, we're sort of changing, looking in time. We're now measuring in frequency steps, and we can think of frequency also in terms of depth. So we modulate at very high frequency. The thermal wave is only penetrating close to the surface, and at low frequency, the thermal wave penetrates deep into the surface. So we get depth information by looking over a range of frequencies. And the model now is fitting phase versus frequency. Essentially, it's the same mathematical model, but we're just fitting it a different way. And again, by fitting this curve, we can obtain the unknown thermal properties that we need. So this example in this figure is a type of PCB, for example. That would be a good option for the low frequency FDTR. Okay, so because these are transient techniques, the depth probe is related to the thermal diffusivity. So thermal diffusivity is proportional to thermal conductivity, inversely proportional to the heat capacity, this alpha parameter, and it tells us about how quickly heat diffuses through a material. And so from the thermal diffusivity, we can calculate for both techniques as a function of time or frequency what the thermal penetration depth is. So at a certain time or certain frequency, what the thermal penetration depth is. This is an approximation, but it is a good guideline. And that's illustrated on the right-hand side. So we take a piece of silicon, we measure the two different techniques. So nanosecond TDTR takes us up to microseconds, which is tens of microns below the surface. And the FDTR is kilohertz down to tens of hertz. So probing deeper into the sample. Okay, so how do we determine the parameters we need from the measurement data? So we take those plots, so time plots or frequency plots for the two different techniques, and then we're fitting a analytical heat diffusion model, which is axisymmetric. So that means that we assume that heat diffuses equally in all directions, and then for multiple layers up to layer n, we can input the known parameters. So here we have K R, KZ, so in-plane, out-plane thermal conductivity, for example, and input the known parameters, and then we fit the unknown parameters to get a best fit to the experimental data. So yeah, I'm not going to go into the mathematical model, but if you're interested, there's a good review paper here from Jiang, 2018, this reference below. So behind the scenes, what's actually happening is there's a Monte Carlo algorithm which is doing the fitting. So this, so the errors you see reported are actually the result of multiple fits where the parameters are varied slightly. So the known parameters, the control parameters, are varied slightly within a preset distribution, and that's what's used to estimate the uncertainties, the errors in the fitted parameters. And that's is kind of the gold standard really in terms of error estimation for robust error estimates. Okay, so another important concept is sensitivity analysis. So I mentioned before that we can measure multiple parameters simultaneously, but to do that we have to have the two parameters have a distinctly different response in the modulation frequency all the time, depending on the technique used. So we have a software which will generate these sensitivity plots, and from that you can determine whether it makes sense to fit multiple parameters simultaneously. So in this example, we have the thermal conductivity of two different layers are of interest. So this is a semiconductor chip with a die attach and a heat sink. And we're interested in the die attach thermal conductivity and heat sink thermal conductivity. And from this sensitivity plot, you can see that the response is quite separated in frequency. So you can accurately fit these two parameters at the same time, and that's a useful first step in planning measurement. Okay, so yeah, it's not just thermal conductivity measurement. we can also measure heat capacity, because both techniques at their core are really sensitive to thermal diffusivity. So heat capacity is another parameter that you can measure. So this is an example of measuring a thermal interface material, where the heat capacity of that thermal interface material is of interest. So you could prepare a sample to do DSC measurement, but again, that requires sample prep, and it may not behave the same way as the TIM layer in an assembly that's gone through a certain temperature process. So here we can measure that in situ, which is an advantage. Here, the plot on the right is just showing an illustration of, again, a Monte Carlo analysis. I won't really go into detail about what this means, but essentially it's showing the correlation between the two parameters, thermal conductivity and specific heat. And the closer this circle is to closer it is to a circle rather than the line, it's showing us that the parameters are not correlated. So if these two parameters were well correlated, all the points would line on line, and we wouldn't be able to fit these independently. But at the bottom, you can see that we have a value for the thermal conductivity and the specific heat capacity with associated error bars. Yeah, so this is quite unique, that we can measure thermal conductivity and heat capacity simultaneously for layered materials. Okay, so in the second part of this webinar, I'm going to present some application examples so you can get a flavor of how these techniques are applied. Okay, so starting with TDTR. So starting with a very simple example, so the kind of the bread and butter of this technique really is to measure thin film coatings. So here we have a dielectric layer deposited onto a silicon substrate. So you can see the measurement data on the left-hand side. So again, so we have the laser pulse, heats the surface cools, and then we fit that with the model. And the two things of interest here are the thermal conductivity of the dielectric, which is 5 watt per meter Kelvin, but also the thermal boundary resistance between the layer and the substrate. Yeah, that's just a very simple example to start with of a fairly common type of sample that we would measure. So this is a real application example from a customer. So this was published by Soitec. So they're taking silicon carbide films and then bonding that to silicon carbide substrates. It's a smart SiC technology. The epitaxial film is 400 to 800 nanometers thick, and they're particularly interested in the thermal resistance between that epi layer and the substrate it's bonded to. And then the plot in the center is showing some measurements for films which have been unannealed, so as bonded or annealed, and we measured a large reduction in that thermal boundary resistance. And then on the right-hand side, just an example of doing the measurement at different ambient temperatures. So you can see as the temperature goes up, the thermal conductivity decreases, and you see that's evident in the slower cooling. So we also do whole wafer mapping. So this is an example of a semiconductor wafer where the semiconductor film is bonded to a diamond substrate for thermal management. And here what's interesting is to measure the uniformity of the thermal boundary resistance between the GaN, so that's the semiconductor film, and the diamond. So on the right-hand side is a map over a 4-inch wafer, 4-inch diameter wafer. And in this example, there's no coating on the wafer. So we've chosen a wavelength that's absorbed by the semiconductor film, and we also get a good thermoreflectance coefficient. So this is a completely contact-free measurement, so that wafer can be used afterwards for other tests or device processing. So this is a nuclear fuel example. So this is a triso nuclear fuel particle. So we here, so basically this nuclear fuel particle in the center where it says kernel would be uranium, although in the one that we measured that was another material, inert material. And what's interesting here is to know the thermal conductivity of all these different layers, because heat is generated in the kernel and has to flow to the outside. So we polished it into a cross section, and then we did a line map from the center to the outside. The central plot shows some example measure traces on the different materials, and then by fitting that, we can generate a plot on the right hand side of thermal conductivity versus position, so moving outwards from the center to the outside. And the spatial resolution here was 2 to 7 microns. You may question why the spatial resolution is varying. It's because these different materials have very different thermal diffusivity. So silicon carbide has a very high thermal conductivity. Heat spreads during the measurement, which is why the spatial resolution is slightly worse, lower in the silicon carbide than in the buffer, for example. Okay, so now we're looking at an example for FDTR, so moving on to FDTR. And this is an example of looking at a TIM layer, particular TIM layer, which is the die attach between the chip and the carrier or flange. So in this case, sintered silver was used. And that's very process dependent. So we have two examples which are processed in different ways, and we're interested to measure the thermal conductivity of that die attach layer without having to disassemble the assembly. So on the left-hand side, top left is measurement data for two different chips, which are processed in different ways, and you can see that one has a high thermal conductivity and one has a low thermal conductivity. And then later we X-rayed those parts, and you can see that the one with low thermal conductivity has extensive voids in the sintered silver there. So yeah, that's again, that's a unique thing, is that we can measure thermal conductivity of a layer below the surface. So isolate the die attach layer here, and we can measure really inline. So you can get information like for process control, or or if you're developing a process such here, silver sintering. Okay, so related to that, so this isn't really about measuring the thermal properties, but measuring defects. So here we specially prepared a sample where we have a bonding layer where we've intentionally introduced a void, just for illustration. And we're measuring, what we're measuring here is the heat transfer from the metallization into the aluminium substrate. And by scanning over this sample, you can see where the void is. There's no heat transferred. So this is a little bit analogous to scanning acoustic microscopy, but we're really visualizing actual heat transfer. So it contains a little bit more information which is relevant to applications where you're concerned with heat extraction, thermal resistance. Okay, so then I think this is the final example. So here we're measuring a composite heat spreader. So it's a metal diamond composite, which has a cladding layer. And we'd previously measured these with laser flash, but that gives you no information about the cladding layer or the thermal resistance between the cladding layer and the composite. It gives you an effective average, but the cladding layer is of particular interest because it's known that it could present a thermal barrier. So in this measurement, we use the low frequency FDTR to measure the R2, which is the thermal boundary between the cladding layer and the composite, and K3, which is the thermal conductivity of the composite. And the illustration on the right side, you can see that we can nicely separate those two parameters. So it gives us additional information beyond laser flash, for example. Okay, so just to wrap up, summary of what we've covered. So we've looked at the two different thermoreflectance techniques that we offer. So yeah, they provide high resolution measurement of thermal properties, both in plane and depth information. So depending on the application, we have flexibility in the depth and spatial resolution. Nanosecond TDTR is focused more on the high spatial resolution thin film, FDTR for larger spatial resolution thicker films, both suitable for multi-layered systems. It's configurable depending on the application requirement. Yeah, and yeah, I hope hopefully I've conveyed that there are a wide variety of applications. Yeah, and then finally, so yeah, we're very open to running demo measurements. So if you have some materials that you think this could be useful for, please get in touch. And we look forward to evaluating them. Yeah, and that's everything from me. So thank you very much for your attention.
Awesome. Thank you very much for that, James. So folks, just for the kind of wrapping things up here today, I'm going to kind of go through just a few kind of standard outro slides. And then for those interested, I've seen quite a few questions come through there. So we will be eventually then moving into the Q&A. All right. That, perfect. All right. So yeah, folks, if you're looking for more content on different applications of thermal conductivity, we do have a large variety of kind of past content available on our on our website, different webinars, tech libraries, publications. Definitely feel free to check those out. As a kind of a little announcement upcoming, we do have two webinars scheduled in April. These will be coming back to some of those 101 series. The first one on April 9th, my colleague Genesis Infante from our Thermal Analysis Labs team will be going over DSE methods and applications. And then later on in the month, Alex, again from our TAL group, will be doing a TMA-focused 101 series on methods and applications. So again, these will be more educational-based series, walking you through some of the kind of core fundamentals of these measurement techniques. On that note, as kind of mentioned here, so C-Therm, we are partnered with both Rigaku and Metrovib for North America for their line of thermal analysis and DMA instrumentation, respectively. And our TAL group is a full-service test lab offering different measurement methods for the transient techniques that we offer on our Trident platform, as well as other methods that are available in industry. So, similarly, if you'd like to learn a little bit more, if some of the content was interesting, or again, maybe looking just to see what that would look like on C-Therm side of things, we do also offer technical consultations. Happy to schedule those, learn about your application. In cases like maybe you're dealing with some of the content that James here presented, we'll be certainly happy to direct you to the appropriate location, depending again on what types of samples you're working with. For those looking for some budgetary information, again, maybe on the Trident system, again, if this was something you were interested in, we can also certainly provide that. These quotes are available for free. Just reach out to us and we can accommodate. Also, just a special note, anyone coming from the academic industry, if you're a research graduate in any kind of enrolled school in North America, definitely feel free to mention that in your inquiry. We do have a nice academic support program available just to support those testing needs and instrumentation purchases. Last little kind of request from my side, if you're not already doing so, give us a follow on LinkedIn and also check out our YouTube channel. This is where we post all of the upcoming webinar events, different application pieces, blog posts, etc. If you're looking to stay up to date with us, this is where it all goes first. All right, and that kind of wraps up the kind of formal presentation here today. From my side, this was again really James's show here, and I want to again thank him for joining. It was really great content, kind of seeing the other sides of where these thermal measurement techniques can come in, some very novel applications that is being worked on there. So my thanks to James for joining us, and also to the audience for participating with us here today.